Thank you. All right, hello everyone, I'm Alex. I'm going to be presenting the Name That Neutrino project. I'm a second year here at U of T. I'm studying Astro and CS, and this is a project that I worked on over the summer. So yeah, quick overview. I'm going to start with phase 1 of Name That Neutrino. So that was mostly carried out last year and happened before I arrived. I did this research at Drexel in Philadelphia under Professor Love. And so after phase 1, I came in. I'm going to discuss my contributions, and then I'll discuss what we changed for phase 2. So to begin, what is the IceCube Neutrino Observatory? So this is an enormous observatory at the South Pole. It's 1 kilometer by 1 kilometer by 1 kilometer, so 1 cubic kilometer, which apparently holds about 100 million elephants or 10 million blue whales. So it's pretty big. It consists of many digital optical modules. So there are many strings that go down to the ice, pretty deep. And then there are these detectors that are hung on the strings. These detectors detect radiation that occurs when particles from the atmosphere or even outside our galaxy come in and interact with the ice and produce Cherenkov radiation. And it's located at the Amundsen Scott South Pole Station in Antarctica. Another short explanation of what could be going on there.
Actually built up directed energy weapons platforms operating under the false pretenses of science. That's what's actually going on in South Pole Station. There are technologies and weapons-grade technologies on this planet. The average citizen cannot even begin to wrap their brains around.
Okay, so that's another explanation of what could be going on down there. I choose not to believe that one, or maybe this whole time I was just working on weapons data and I didn't realize. So, okay, the IceCube collaboration. So this is a huge collaboration with many participating institutions from around the world, more than 350 people. I think U of T isn't actually in it. Maybe it will be now. And yeah, they do a lot of cool work. Sorry. So basically what IceCube does is it detects signals from particles. So that's like an artist's rendition. Obviously, the galaxy is not that close. And so these particles interact with the ice and produce these events. And so these event topologies are what I'm going to be talking about today and are basically the data that we were analyzing. So to give a quick overview of what a neutrino is, also to give credit, most of the pretty slides are not mine, they're Professor Love's. Any slide which has a zero aesthetic component is probably mine. So a neutrino, it's a fundamental particle, which is nearly massless and neutral. And so what that means is that it does not really interact with other matter. So fun fact is there's about 65 million neutrinos passing through your thumbnail every second because many of them are coming from the sun and from outside our galaxy. They're very abundant and sort of mysterious, so that's part of what IceCube is studying. Here, some particle physics that I don't really know much about. We can find the neutrinos here. They come in 3 different flavors and they produce different interactions. Thank you. Perfect. Yeah, so we have the electron neutrino, muon neutrino, tau neutrino. I'm not going to mention them again because I didn't really do anything with the different kinds. And then some brief accomplishments of IceCube. So it launched about a decade ago, and they detected astrophysical neutrinos. And then a lot of the work that members of the collaboration do consists of trying to identify where the neutrino sources are. And so they identified sources such as, that's probably an AGN, and galactic centers and stuff like that. So I worked on a very specific subset of the work they do because it's very broad and there's so many members. And so they named that neutrino project, should be coming up. Okay. So what we see when a particle actually interacts with the ice is like the event topology. So all these little spheres here are the detectors that I mentioned earlier that are hung on the strings in the ice. They're basically holes drilled down into the ice, and the ice acts as like a natural detector. Because the neutrinos interact so weakly with matter, they basically have to go through a lot of matter before they're stopped. And so the cubic kilometer of ice provides that medium that would stop them. And then the produced radiation is measured by these detectors. So the 2 basic event topologies are going to be the cascade and the track, and we're going to get into more complicated versions of them. And so the exact shape and interaction will depend on the neutrino flavor, which is what I mentioned earlier, different types of neutrinos. and the type of interaction. And these aren't actually neutrinos going through, like that's not a track of a neutrino, but a track of the particles that are produced when the neutrino interacts with other particles. And yeah, that's what it says, from weak interactions of neutrinos with the ice. Okay, so the motivation behind the Name That Neutrino project is that there are several data levels to what IceCube sees. So level 0 is the trigger level data. And what that means is that anything that triggers a detector is a level 0 event. So that's what Name That Neutrino focuses on. MC is Monte Carlo, which I'll get to in a bit. And so basically the data that Name That Neutrino uses isn't actually produced or collected from the detector, but it's generated so that we know like the answer to what event topology is. So what we're going to see is that there's a Monte Carlo truth, which fits each event into one of 5 categories. And the data used in the phase 1 had a uniform energy distribution. So basically why I'm saying all that is we start with level 0 data, and then there's a lot of background filtering, reconstructions, processing, and we get to level 2 or level 3 data, which is what most of the scientists are going to do their analysis on. It's much cleaner. And so we're going to get to that in a second too, the DNN, the deep neural network. So there was one of the collaborators trained a neural network on level 2 data. And you can see the amount of data he processed, 13 million events. And then Corsica and NewGen are the different kinds of simulations that were used. So see, okay. So more of the motivation, there's about 30,000 or 3,000 events per second at the trigger level, so at the most basic level. And most of them get filtered out to only about 10 events per second at the analysis level. So basically what the Name That Neutrino project was investigating is sort of, is there anything useful in the trigger level data since there's so much more of it? So it'd be nice to see if we could use that more rather than just cutting it out. So here I'm going to show you the first example of an event and what you'd see in the project. So what it says here is that the neural network is going to predict a track that kind of goes through the detector. The expert predicted a track that goes through the side, so that's a skimming, and I'll cover these again in a second. And the user also predicts a skimming. So if you see this, the line on the edge of the detector here, oh, let me pause the video. Okay, so this line here is a skimming event, because basically that means that a particle came in and barely grazed the detector, so all the energy seems to be found in just a single line. So basically what I was just saying is that the humans classifying it all were able to understand that this is a skimming event, but there are some limitations to the machine learning techniques used so far, because it thought that it was a completely different event. Oh, I might have escaped. All right. Okay, so back to the different kinds of events. The primary one of 2, is a cascade. So that is essentially a large ball of these detectors lighting up in one spot, and the rest are tracks. So the skimming is this track on the side where they all kind of line up on the edge of the detector. A through-going track is a track that starts on one side of the detector and exits out the other side, and it is what it sounds like. It goes through the detector. A starting track is a track that begins inside the detector, because a neutrino is able to get inside the detector without interacting with other matter. So the event is able to start within the detector. And then a stopping track is a track which ends in the detector. So here you can see it. It kind of starts at the edge and it ends before getting to the other edge. So these are the 5 kinds of event shapes that were classified in the Name That Neutrino project, and it's what we focused on. So basically the project was sort of a citizen science project, in that it was a form of like science outreach. So it was hosted on Zooniverse. It's a web-based platform for researchers, and there are over 1 million volunteers. Some very famous projects like Galaxy Zoo, where users could classify different shapes of galaxies. And it helps a lot with this kind of, to streamline this kind of research. Some statistics from the first phase: there were 2,000 volunteers, 170,000 classifications, thousands of subjects, and they were all completed. So basically what happens is volunteers will go into this website, log in, they'd get a bunch of the videos like I showed you before, and they'd get prompted to select which kind of event they were. And then they would classify the event. Each event got classified up to 40 times. And then we took that data to see how good were the users, how good was the neural network, and what results could we draw. Okay, so to get into the neural network, so we call it the DNN, the deep neural network. It basically treats each event as like an image recognition task. So I believe it was a convolutional neural network. Um, so the events get sent in as 4D images because of the 3 spatial dimensions of the time dimension. And it was trained on these Nugent and Corsica data sets, which are all like artificial data sets. So basically the Monte Carlo simulator would simulate an event that could occur inside the detector. And then the neural network was trained on that. And so if I go back to this slide, we saw that the neural network was trained on higher level data. So another aim of the project was to see if it could accurately classify like noisier, lower level data. Some more technical information, which maybe isn't that important. It basically uses deep learning to create event classification. It had a bunch of time and charge features, which are sort of embedded in the videos, but maybe the users don't have explicit access to. So basically, um, in a video or in a picture such as this one, the larger that the bubble is, the more charge or energy that was received at that detector. Um, so the neural network has access to the size of all these bubbles, whereas the user kind of has to see that visually. Okay, and now a couple important features about the neural network. So maybe I'll write this out on the board a bit. We basically had uh, 5 possible categories. So the way that the neural network works is that it predicts the likelihood that the event is in each of the 5 categories. So that's why you'll see at the lowest level over here is 0.2, because at minimum, like the most split that it can be in its decision is if it gives each one 0.2. So basically the way this works is that it gives a confidence level for each thing, each category, and it all has to sum to 1. And this is sort of supposed to represent the likelihood that the event is category 1, 2, 3, 4, or 5. So the distribution does not really look like 0.2 for each one. It mostly looks like 1. So what you'll see if you look at the data is that it's like, okay, I think it's 0.999% likely to be 1, and then more or less 0 for all the rest. So this is sort of to be expected, because when you train the neural network, you're incentivizing it to be confident in its answers, and you basically want it to give you, ideally it would give a score of 1 to all the correct answers and 0 to the rest. And you're sort of trying to get to that ideal. So as you'll see, it has mostly confidence of 1 for the events, and that's about half the events, or a third, and the rest drop down pretty sharply. Then the users are a bit of a different story. So at the bottom here, it says retirement limit. That's just the amount of times that each event was classified. So we didn't know how many classifications we'd receive at first, so it just started at 15. And then once every video was classified 15 times, it was up to 20, 30, 40, 20, 25, 30, 35, and then 40. And so what you'll see is the user consensus like vote fraction. And so what that means is like for the highest, so the users would each vote for a category. So maybe like category 1 would get a vote, and a second vote, and then 2, 4, and then a third vote. And it's basically what's the highest fraction out of the total votes. So disappointingly enough, the users really disagree, at least at level 15. And so you'll see that there's only about 0.4. So maybe 40, the category that won got about 40% of the votes, and the remaining 60 was split amongst the rest of the categories, which isn't a super confident voting scheme. And so I guess what was hoped is that by increasing the amount of classifications, that this distribution sort of shift to the right and that the users would get more confident. But as I increase the amount, you can see that they essentially get less confident. So they're sort of regressing to a mean of like 0.4. And basically what that means is that the users are really split on many decisions, which makes sense because a lot of the events are hard to distinguish, as we'll see. And they're not very confident in their answers. Okay, these are the confusion matrices that show the results. So I'll take a second on these because they're a bit confusing at first. Basically what these are a 5 by 5 true positive, false positive, true negative, false negative grid. And so what I mean by that is that at the bottom here, we have like the hypothetical truth, which is created by like the simulator for the data. So it tells us that there are 339 skimming events, and here is the machine learning algorithm. So out of the 339, it said that 319 were skimming, and then it misclassified the rest. For Cascade, there were 241 events total, and it got 234 of them, and so on. 509, it got 405. So, and the intensity of the blue is how correct it is. So as you can see, the neural network is actually doing really well, even though it's trained on more clean data. Now it's being applied to worse data. So it's averaging, I think the number was 82% on all the data. And it's doing really well on some of them, like 97%, not as great on some, like 80. The users are a bit of a different story. They essentially suck because over here they're doing 10%, 36% right. They're pretty good at cascades, which are the large balls, because they're sort of easy to see versus the tracks. And then they're doing okay on skimming and through-going tracks. Essentially, the problem is that visually it can be hard to tell if a track started in the detector, if it stopped in the detector, if it went all the way through. And so they're sort of struggling in this area. And then this is the user versus the machine learning algorithm. The two plots just different. This is the retirement limit again, which is how many times the video is classified. So you don't really need to care about both of them because they're about the same. And so as you'll see, they agree a lot on cascade events, and the tracks are going to be mostly where they disagree, with a starting track having a low of 9%, and then the skimming and through going are about 70. So basically, okay, this is where I came in. So the issue that we see here is that there isn't a single category for which the users are more accurate. They get pretty close in cascades, and then everywhere else they're about 10 to 70% worse. So it kind of begs the question, like, what are they useful for? And so essentially what I started looking for is we need to select events for phase 2 to run the trial again, but the users aren't very useful. So we need to identify areas where they could be useful. So clearly it's not going to be in any specific category because they're worse at every individual one, but I was trying to look for any area that they could improve on. So I started with the machine learning, the baseline results. So the very nice numbers where it basically gets everything right. And I want to see where does it start to get things wrong. And so what I used for that was this confidence result, the confidence score. And so that's what I was saying over here, which is like 0.99 basically means that it thinks there's a 99% chance it's going to be 1, and the rest follow after that. And the cut here. Oh, it's kind of at the bottom. Can I make this go away? Maybe I'll zoom out for a second because these labels are at the bottom. Basically, on the left is if it's more than 0.9% confident. On the right is 0.99. So if we go back, you can sort of tell by how dark the blue is that it gets much better. So from the baseline, skimming goes up 7%, the cascade goes up to almost 100%, it's at 99.6, and the rest follow. So basically, as you'd expect, as you'd hope, as the DNN gets more confident, it also gets more correct. And I tested that all the way up to like 0.995. Here, there's some errors because there aren't that many classifications here. There's only 3, so it looks like 33%. But it's essentially 100% correct on everything else. So what I kind of concluded was there's no need to ask the users for their opinion if the machine learning algorithm is that confident, because they're not going to be 100% correct. So it's more interesting to focus on the low confidence results. So I can't really see what I put at the bottom. Okay, this is already less than 0.9. So it's most of the data, because I think 90, maybe it's like about half the data. And you can see that based on like how light the blue is, it's already taken a huge hit in accuracy. So now it's only getting it right about 60, 60, 50, 70% of the time, which is closer to what the users are. So that's kind of better for us. And then as you continue to reduce its confidence, it continues to get worse um, until about 40 to 50. So the users are on average 60% accurate. So that means that if we can find these events and the users are actually doing better than the DNN here, then they could be useful. So essentially what I did was I went through the web just looking at Stack Overflow and whatever there was to find how to visualize this data. And what I found was these reliability diagrams. So these turned out to be sort of important. Basically on the x-axis, we have the, not exactly predicted, but the actual confidence of the DNN. Is that going to show? That's not going to show. Oh, it shows over here. So this is the accuracy. So what this tells me is that when the DNN is, let's say a good data point, 0.6% confident, so it's saying there's a 60% chance that the event is X, Y, or Z, then it's a bit more than 60% accurate. So this gray line here shows that what would happen if it were perfectly calibrated, which means 0.99% confidence means 99% likely to be correct, and 30% confident means that there's a 30% chance it's right. So if these points are above the line, it means that the whatever is guessing is underconfident, so it's actually doing better than it expects to do. And here it's below the line. So that means that the DNN is telling you, oh, I'm about 40% accurate here, or 30, and it's actually a bit lower. It's not doing as well as it says it is. And the users are essentially above the line because they just tend to disagree with each other a lot, but they tend to get it right by a small margin, which is to be expected. And also note that the users only vary in accuracy from about 0.4 to 0.8, 0.7 versus the DNN, which spans the whole 0.2 to 1. So that turns out to be important in a second, because then I started looking at um, the truth versus, so these are users versus truth, and what's changing between each one is the DNN confidence. So when the DNN confidence is less than or equal to 1, that's all the events, because it's never 1. Uh, and the user agreement, which is the highest percentage of vote that they got. So that's this idea of like 1, 1, maybe this one gets 3, so that's 3 over 5. So at first I don't touch anything, and these are just the baseline results for the users. So pretty bad. Then if you reduce the DNN confidence, the results stay about the same, which maybe isn't super inspiring, but it's kind of good, because what I sort of expected was that when the DNN confidence goes down, so on this graph when it goes sort of in this direction, that the users would also get less accurate, because maybe just the events are harder to classify. But what seems to be the case is that some events are hard for the machine learning algorithm to classify, and the users are barely affected by this. And so the other thing that we were investigating is the effect that the user agreement has on how accurate they are. So if I go back one slide, the graph on the left shows the user agreement just at a minimum of 0, and here the minimum is 0.55. So the only one that really changes, the cascade goes up to 95%, but the rest are mostly unaffected, which is also kind of good because the users are only more than 0.55. They only agree with each other that much half the time, maybe less than that. So you're not cutting out too many events. And so what I eventually came up with was this. So this is very similar to the other plot I showed. To go back to that, on the x-axis here, I have the predicted confidence of each classifier. So that's either the user or the machine learning algorithm. On this one, it's just the machine learning algorithm. So what that means is that we're checking how confident the machine learning algorithm is, and then we're seeing the same trend as before, that it's a bit underconfident here, etc. But the users remain about level no matter how confident the NN is. So essentially, this region is what's important. I put some error bars on it, which kind of mess it or make it less easy to read. But even the error bars don't cross, so that's good. What this means is that the users are about 60% accurate when the DNN is less than 0.5% confident, and the DNN is only about 20% accurate when it's less than 0.5. So that means that this is a concrete area where the users are more useful than the DNN. And it's also important because if we feed in an event, we can easily get the DNN confidence from this. So about 0.5 or 0.9 or 0.6 or lower, 0.3. So that basically tells us that maybe there's some classification scheme where we can say if the confidence is less than 0.5, give it to a user. And if it's 0.9, don't even let the user see it because the DNN definitely has it right. So just to cover that one last time, that's basically coming from here. I chose 0.55 because it's essentially where they intersect and it's a nice round number. And so the users are more accurate when the machine learning algorithm is not confident. And when it is confident, there's no need to give it to the users because they're much worse and it's essentially getting it right every single time. The difference between the graphs is just the binning of the data, so it's not too important. But basically, how many events are in each bin, or how many bins are on the x-axis. I redid the graphs just with the quantile, so that's the bottom 10%. This is a 10 bins, so the bottom 10% are here, 20, 30, 40, etc. And then also it's 25, and you get the same trend. The reason this is sort of important is because there aren't that many events over here where the DNN is less than 0.5% confident. So I was wondering if this is, oh, if that's just like 20 total events. I was very excited by this little divergence here, but I was wondering because this is only for events with less than 0.5 confidence from the DNN, which aren't too many. So when you redo it, where there's here now there's the same amount of events in each dot, and the trend still reappears somewhat. So that's good. All right, so basically the idea that this gave me is to create a meta classifier. So yay, it does seem like there's something that the users have to offer. And already a basic heuristic to improve accuracy from the graph that we saw is what I was saying here. Screen for DNN accuracy less than 0.5. If it is less than 0.5, send it to a user. And if it's higher, which is most of the time it is, you send it to the DNN. Just based on that, I did some quick math. It's about 84% improvement to 84%. The DNN is at 82% already, so it's not amazing, 2%. But the other idea is that we could use another level of classification, which would take into consideration the DNN output and the user output. So basically, to sort of draw that, this would involve feeding in an event. So this little image of dots. And then here you'd get the DNN data. So it'll tell you, I think it's 0.99% chance to be 1, 0, 0, and like, I don't know, 0.01, 0. And then you'd also feed it to the users. And from the users, you would get their vote. Maybe they think it's 2. And then their user agreement is the other piece of data you could get. So they didn't agree too much on this one. The max was 0.3. Then you feed this into another layer, and this will give you the output. So in this case, the DNN had 0.99% confidence. The users had about 0, or the minimum amount. And so we'll say that it was type 1. But maybe it would learn to recognize that if this were something like, I don't know, 0.4, 0.2, 0.1, 0.30, where the max is 0.4, and the users voted that it's, so that would be event 1, and the users voted it's event 2 with confidence 0.5, then maybe instead of spitting out 1, it would spit out 2. So that was kind of the hope, to create a meta classification system which would use all the data and ideally improve past the baseline. So the DNN starts at 82% accuracy for all the classifications. So to do some proof of concept, I created a decision tree, which basically is a structure that looks like this. So this is a specific machine learning algorithm. And I use the following data, which is basically what I said here. The confidence for the DNN confidence for skimming, cascade, throughgoing, basically for all the events. And then I tacked on at the end the user vote and the user confidence. And the hope is that this algorithm will see some sort of pattern in the data, and it'll decide whether to take the DNN max value or the user value. Nowhere am I telling it pick the maximum value with that the DNN gave, or that this is a vote and these are confidence levels. I just sort of passed it in and let it do its thing. And a decision tree is a structure that looks like this. Right, each level, it has a heuristic to split up the data. So maybe level 1 is like DNN confidence. Is it greater than or less than 0.5? So in tiny font there it says true or false, which is an example of that. And then maybe pass it to this branch, and it says, are the users greater than or less than 0.5 confidence? Take the user vote, take the DNN vote, and so on. And it's sort of like, it's called a decision tree because it's like a decision model where you take in a couple heuristics and you try and make the best decision. So the preliminary results yielded 80% accuracy. So that's pretty bad because it's worse than the baseline that we're using, 82%. And so I used some like pre-built methods to tune the parameters. And the best decision tree I was able to create, the tree structure that I showed, had an accuracy of 88%. So that was pretty cool. That means that already I was able to improve by 6% on what the DNN can do simply by integrating the users. Until I realized, I'm not sure if this is on the next slide, that I was overfitting the data. What that means is that, what's the best way to explain it? Basically, this is the importance that it places on each feature. And so it placed an importance of, these all sum to 1. It placed the most importance on this feature. But this is not the feature in which the DNN is the most accurate. It's the one that occurs the most. So basically what it's saying is that it would essentially ignore the users. So this is a user vote and the user agreement. And all it would care about is which is the most likely to occur. So it's not doing anything interesting. It already knows that there are a total of there are maybe 4,000 events, and event 1 occurs this often, 2, 3, 4, 5. And so it's more biased to pick 3 because it occurs more of the time, and so there's a higher chance it guesses it right. So that's what I mean by overfitting. It memorized the data instead of learning anything about like actually predicting. So here that is again. The event with the highest count was event 3, which is the most important one, but it has one of the lowest accuracies. So if I tell you like, I'm giving you these 5 numbers, and the second one's the most accurate, you're going to want to place most importance on the second one. But it learned that the third one is most likely to be correct, so place more importance on the third one. If that makes any sense? And then it is essentially ignoring the users because, as we know, the users aren't great. But I'm trying to get some model which actually incorporate the users because they do have some use. Sorry, skipped ahead. Okay, so here I just did another deep dive on Stack Overflow, came up with 4 buzzwords for machine learning models and put them there. So the decision tree is the one I started with. AdaBoost is a model that uses a bunch of really bad classifiers and puts them all together, and it ideally creates something better out of that. And so it doesn't overfit as much, doesn't learn the data as much, because each classifier isn't as useful. A random forest is sort of a play on like a decision tree, where you, instead of having one tree like that, you have a bunch of them that all decide together. And then I won't get into the other one, gradient boost. Basically what I did is I just took higher level machinery and threw at the problem. And so the baseline results are shown there. The decision tree is pretty bad, as we saw, but the others are doing pretty well. And if you note, let's say AdaBoost, which I think was the best one in the end, it places 0.3, which is the largest importance, on event type 2. And if I go back a couple slides, so either to here or to here, the DNN accuracy by event, it's the highest for event number 2. So that's good. It means that it's learned to trust the most trustworthy vote from the DNN, and it's not falling for like category 3, which would show that it's just memorizing the data. And so in the end, I kind of settled on these two. The random forest got up to an accuracy of 94%, but it was likely overfitting because the whole event 3. And I'm kind of running out of time, so I won't get into that. And then essentially this is all proof of concept, but I ended up with an accuracy of about 88%. So plus 6%, not terrible. And it sort of shows that there is some utility to having users do these classifications and that it actually does add something. So a small summary there is that AdaBoost essentially places the feature importance in the desired order, which is relative to the accuracy of the DNN. So that's the conclusion, basically. The users can significantly contribute, 6% maybe, to the DNN classifications. And so what we did for phase 2, there were many other cuts made to the data that I wasn't exactly a part of, such as events with lower energies aren't classified as well by the DNN because it has these like numbers instead of visual cues for the energies. Kind of messes it up, so we went for those. But one of the most important cuts was that the events with less than 0.5 DNN confidence were the ones that were selected. And what's also important about that is that that heuristic is really easy to obtain because you take an event, you run the model on it, and you immediately get that confidence number. And so that allows you to select events pretty quickly. And so now, some slides credit to Professor Love, but phase 2 has launched pretty recently. So to take a quick look at that, this is Zooniverse, the website I was telling you about. There's some information about the project here, Professor Love, but the interesting button is going to be classify. So that takes me here. There's a little tutorial. That's the background of the Ice Cube lab. I'll just hit continue. It tells you that there are going to be cascades, tracks, and skimmings, starting, through going, stopping, etc. So if you guys want to see what it looks like to actually contribute to the project as a user, you can just go to Zooniverse and type in name that Neutrino, and you'll come here. So maybe an example, just to see what that's like. Okay, so does anyone have a vote on what that might be? I don't know if I explained them all very well. Which one? Okay, maybe. I would, basically what I'm going off of, I didn't actually do many of these myself because I was just looking at like the metadata, but I would guess a skimming because they're all sort of on the edge here and like piled on top of each other. The annoying thing is there's no automatic feedback because of how it works. So I send that in, and then the next person who works on the project will analyze my data, I guess. So to do another one, some of these aren't very clear. So the red dots are the ones that occur first to give you sort of time cue. And I'm seeing a bunch here. So I'm going to guess that that's a through-going track because it's hitting this side and going at the other side. And so I'll send that classification in track. And I'll select through-going, identify, done. So that's phase 2. I'm not sure how long it'll take, maybe a couple months to get all the classifications in. And then we'll analyze that data and see what changed. So that's all I had. Thank you very much. I guess questions, or if anybody has any questions.
Okay, so if anyone has a question, no?
Yes.
Thank you for the presentation. So I'd like to ask about your like incorporation of user input into the DNN.
Uh-huh.
Do you think it would be a good idea to sort of pre-train a model on what kind of tracks or event topologies that the users are good at detecting and use like the results of that like pre-trained model along with the DNN? Would that like have you considered that? Would that improve?
Say it again. You're saying train another model on
Uh,
the lower level data?
yeah, well, I guess so. Yeah, I guess train a lower level model or a
Mm-hmm.
model on uh like take users data or like
Okay.
user input
Yeah.
and kind of figure out what type of events that the users are good at classifying
I
and
see. Yeah.
only consider their input for those kinds of tracks.
Okay. Yeah, that does make sense. That's kind of like the idea of what we're going for.
Right.
Basically, I tried to include the DNN too, because it's just more accurate, so kind of boost the numbers.
Right.
But that's definitely another way. You can probably integrate the meta level into any of these other levels. So I think that also makes sense. Yeah.
I see. And another question I had was
Mhm.
about the error bars on your reliability
Yeah.
graph. Uh, could you explain how you kind of calculated those error bars?
Yeah. I think these are. Yeah, if you Google wall errors, I forget the exact formula. It might just be the errors for statistical whatever it is, like the z-score and probability, stuff like that. But maybe more interesting is I didn't really explain the binnings too well. So what this does is in order to see how accurate it is, you can't, I can't give you an event, and if it got it right or wrong, and you'll tell me how, I can tell you how accurate it is there, because they either got it right, which is 1, or wrong, which is 0. So you kind of need to create these bins. So from 0.9 to 1, all events that fall in here, we take, and then we see how many got right from 0.9 to 1. And so that would be like that bin. And then the more events that were in there, the more confident we are that that was like its true accuracy, hence the error bar. I'm forgetting the exact formula right now, and I tried with a couple different formulas. And so yeah, and then from here, 0.8 to 0.9. I think they might also not be exactly aligned on the x-axis because where it lies in the interval is the average confidence in that interval. So that's maybe an additional layer. But yeah, and then here the error bars get huge because there are essentially 0. There are very few events where the DNN has less than 0.5 confidence. So these are very large error bars.
I see. That makes sense. Thank you so
Mhm.
much.
All right, yeah, going back to I think the beginning of the presentation, you're talking about like how the neutrinos don't really interact with matter. So
Mhm.
then I was kind of curious how the detector is able to like um, slow it down fast or enough to be able to
Mhm.
detect them.
Sure. I think it's essentially statistics, or you get enough neutrinos. I'm not sure what the best slide to pause on is. Maybe here. You have a cubic kilometer of ice. I'm not an artist, so I'll just leave it as a square. Maybe like this. And a lot of the neutrinos are just going to go straight through, and they're not going to interact. But you're getting so many, like we said, 65 million just through your thumbnail, that some of them, even though they interact very rarely, they will interact. So it's basically a numbers game. You get so many coming through that eventually one of them will hit something, and then it'll produce a shower of other particles. And these are more likely to interact. These might be like muons, or I think that's essentially what the most likely thing to get produced. And then these particles will interact more with the ice, and that'll light up like the detector that's on this string. So basically, you get so many events, so many neutrinos coming through, that even though they interact weakly, because they barely interact, eventually they will.
All right, thank you for answering those. If there's no more questions,
Probably is.
well, I think we're all good. Thank you
All
so
right.
much.
Thank you too.
And can I have a warm round of applause for our speaker?
Thank you.